Hi everyone, my name is Nia Salihovic, and today I'll be walking you through the foundation of our project, SMS spam detection, starting with our proposal slides. We will start off with slide 2. This slide can be seen as our motivation. The idea behind our project came from a real-world problem, the constant flood of spam text messages. They're not just annoying, but sometimes dangerous, especially when used for phishing or scams. With so many people relying on SMS for communication, we saw this as a great opportunity to build something useful. Our motivation was to create a model that could automatically detect and filter out these spam messages before they reach the user. Moving along to slide number 3. This can be seen as a problem statement. The main problem we wanted to solve was how can we teach a computer to differentiate between spam and legitimate SMS messages? The challenge is that spam can take many forms, and simple rule-based filters aren't flexible enough. So we needed a smarter, data-driven solution that could learn patterns from a real data set and make predictions on new messages. Moving over to our fourth slide. This can be seen as our data set and tools. In this slide, we used a public data set with around 5,500 SMS messages labeled as either spam or ham. This helped us train and test our models. For our tools, we use Python along with libraries like Pandas and NumPy for data processing, Seaborn and Matplotlib for visualization, and then TensorFlow and Keras for building the machine learning models. This tech this tech stack gave us everything we needed to prepare, train, and evaluate our spam detection system. That's a brief summary of the motivation, the problem we addressed, and the tools and the data we used to tackle it. Thank you.
Hi everyone, this is Shishant. Now I'm going to explain the remaining slides, which is expected deliverables. In first, that is pre-processed dataset. We begin by cleaning and preparing the SMS dataset to ensure consistent and meaningful feature representation. This includes text normalization, tokenization, and handling class imbalance, etc. And the second is baseline model evaluation report. This is our first step in model building where we apply a simple machine learning model. The evaluation includes a confusion matrix to visualize true positives, false positives, true negatives, and false negatives. And also, this report helps set a reference point to measure improvements from more advanced deep learning models. And the third one is trained deep learning models. We developed advanced models such as LSTM or CNN based neural networks tailored for text classification. These models include customized text vectorization and embedding layers to understand the semantic meaning of SMS messages. And the fourth one is comprehensive model evaluation metrics. For every model, we evaluate using key metrics, accuracy, precision, recall, and F1 score. This allows us to understand not just how often the model is correct, but how well it handled imbalanced data. And the last is relevance to project goals. In these deliverables collectively aim to determine the best performing model for SMS spam detection. And the next is evaluation methodology. We evaluate model performance using accuracy, precision, recall, and F1 score. Accuracy tells us overall correctness of model. Precision shows how many predicted spams were actually spam. Recall indicates how many actual spam messages were correctly identified. F1 score combines both precision and recall to give a balanced performance measure. And also, we focus on imbalanced dataset focus and also F1 score for model selection. This comprehensive evaluation ensures we identify the most effective model that generalizes well and performs reliably in detecting SMS spam. Now my teammate will continue.
Hi everyone, my name is Nia Salihovic. Now let's dive into our Jupyter notebook, where the actual implementations happened. I will walk you through cells 1 to 13. In cell 1, we can see that we began by importing all of the necessary libraries. This includes tools like pandas for handling data, NumPy for numerical operations, matplotlib, and Seaborn for visualizations, and also TensorFlow and Keras for building the neural model, network model. In cell number 2, moving over, next, we loaded our data set using pandas. We specified the Latin-1 encoding because the file had special characters. After that, we displayed the first few rows of the data set. We noticed that while there were 5 columns, only the first 2 were useful. One for the label, spam or ham, and one for the actual message. In cell 3, this is where we started to clean things up. To clean things up, we removed the extra columns that were empty. We also renamed the useful columns to something more descriptive, such as label and text. Then we created a new column called label_enc, where we mapped ham to 0 and spam to 1. This numerical format is better suited for machine learning modules. Moving down to cell 4. In cell 4, we check the distribution of the labels using value_counts, parentheses open and closed. This shows us that the data set was imbalanced, meaning there were a lot more ham messages than spam ones. That's important to know because it can affect how the model learns. We are now moved down to cell 5. In cell 5, this is to visualize that imbalance. We plotted the class distribution using Seaborn, as you can see. It gave us a clear picture of just how skewed the data set was, with ham messages dominating the data set. Let's move down to cell number 6. In cell number 6, we then moved on to text pre-processing. We defined a function that cleaned each message by converting it to lowercase, removing punctuation, and filtering out common stop words. This helps reduce noise in the data and focus the model on the most meaningful words. In cells 7 and 8, right here, we applied that cleaning function to every message in the dataset. This gave us a cleaned up version of each message, which we stored in a new column. We also displayed a few results to confirm that the cleaning worked as expected. In cells 9 and 10. In cells 9 and 10, now that the text was cleaned, we needed to convert it into numbers. We used Keras tokenizer to assign a unique number to each word, then padded the sequence so that all inputs were the same length, which is a requirement for feeding data into a neural network. Moving along to cells 11 and 12. In cells 11 and 12, here we define our model architecture. It's a simple neural network with an embedding layer to learn word relationships, a global average pooling 1D layer to reduce the output dimensions, and dense layers for classification. The last layer uses a sigmoid activation to output a probability between 0 and 1, this indicating whether the message is spam or not. And in cell 13, finally, we can see this is where we compiled and trained the model. We used binary cross entropy as the loss function and Atom as the optimizer. The model was then trained on our process data, and we monitored how well it was performing with each epoch. That wraps up the key steps in our notebook, from loading the data and cleaning it, to building and training our model to detect spam messages.
Hi, this is Sushant. Now I'm going to explain the remaining code. This line of code is performing text classification on spam dataset using multinomial naive Bayes model. It loads a dataset, pre-processes it, and split into training and testing sets, vectorizes the text data, and also calculate evaluation metrics like accuracy, precision, recall, and F1 score. This line of code shows the result of applying the text vectorization layer to the sentence. This is SMS spam detection AI final project. This line of code initializes an embedding layer for neural network using TensorFlow's library, which maps each word in predefined vocabulary of a specific size to 128 dimensional vector. And this line of code constructs a neural network model using TensorFlow API designed for binary classification of text data. And also the model begins with input layer that takes in strings, apply text vectorization layer to convert these strings into integer sequences. This model 1.summary displays a summary of neural network model providing details about each layer, including the types, shapes, and number of parameters in the model. This code builds a TensorFlow model for classifying text data. It starts with an input layer that accepts string data, processes it through a text vectorization layer, and convert text into integer sequences. The model incorporates a global average pooling layer to simplify the output from the embedding layer and dense layer with ReLU activation for learning nonlinear interactions. And also it concludes with an output layer using sigmoid activation for binary classification. This Python script defines three functions for managing a machine learning model using TensorFlow's framework. The compile model function sets up the model with Adam optimizer, and the fit model function trains the model on providing training data for specific number of epochs, validating performance on text data. This evaluation model functions access the model on given data, calculating the metrics like accuracy, precision, recall, and F1 score. This line of code constructs a more complex neural network model using TensorFlow API for text classification. It begins with an input layer for string data, followed by vectorization layer to convert text into integer sequences. And also it includes bidirectional LSTM layer with 64 units each and passes it through a dense layer with ReLU activation. Finally, it ends with output layer using a sigmoid activation function for binary classification. This code utilizes TensorFlow and TensorFlow Hub to create a sequential model for text classification, incorporating the Universal Sentence Encoder to embed techniques input to numerical vectors, followed by dropout regularization and two dense layers for classification, ultimately training the model over five epochs, which is mentioned here. This final code evaluates the performance of multiple models like multinomial naive Bayes, custom vector embedding, bidirectional LSTM, and transfer learning with universal sentence encoder on test dataset, which shows the result into data frame for comparison, accuracy, precision, recall, and F1 score. By comparing all these models, we got the best model USC transfer learning model with 98.1% accuracy and the same bidirectional LSTM model with 98.1 accuracy, but the custom vector embedding model gives 60% accuracy and the same goes with multinomial model 96% accuracy. Thank you.